Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi guys, welcome to the Integrative AI panel. People are still trickling in, but for those of you that happen to not be here in the room for the previous session, this panel follows a plenary session that had the same topic of Integrative AI. And we have a fabulous group of researchers here from, I guess, your left to right, Eric Horvath from MSR, Charles Rich from WPI, Manuela Veloso from Carnegie Mellon, Li Dong Zhou from MSR, and Larry Zidnik from MSR. First, I want to thank them for agreeing to be in the hot seat today, I think, on this, what I believe to be is a really, really interesting topic. And before giving them the floor, I'm just going to spend 1 minute on kind of setting up the topic a little bit. There's this a bit intriguing title of Integrative AI, and we're all maybe struggling a bit. What does that exactly really mean? And I like the term Ken, I think, used yesterday, which was organism. I think we're onto something. This idea of building systems where we leverage different kinds of, we harness different, bring together different kinds of competencies to create things that are more than the sum of their parts is I think, an interesting idea that merits more thrust and exploration. I was looking actually this morning at the definition, at the dictionary definition of what a system is. And apparently a system is a regularly interacting or interdependent group of items that form a unified whole. And I think to Eric's comments, at the beginning of the previous session, over the years, there's been a lot of, energy and a lot of work spent into advancing state of the art in these various vertical fields like vision and speech and language, subparts of AI. But I think it's interesting to think about how can we bring them together? How can we get more of this interdependence going? Like Larry had a fabulous talk before on vision and language. I think we all have intuitions that there's potential big benefits here. Multimodal fusion in the multimodal interaction community. People for years have worked on shown how robustness can be increased and created in these ways. But I think there's also really important challenges and big challenges in creating this kind of unification. So the hope is that with the panel today we'll discuss some of these topics and get to some of these intuitions and hear their reflections, and also maybe get some educated guesses about directions we should pursue more and where we should push on the accelerator more as AI researchers. Just a last word about mechanics. I would like to make this as interactive as possible. So I'm going to, in a second, give the floor to our panelists to do a little sort of introduction and initial reflection. And after that, I do have a list of topics that I consider would be interesting, perhaps, to go through. But I would really like to open up the floor to the audience and get many questions from the audience and participation. OK, so with that, I think I'm going to pass it on to you guys. I don't know if we want to start right to left, or we can start with Eric right here. I think what would be, just to kick it off, like maybe spend, I don't know, somewhere between 3 and 5 minutes. The first thing I would like you to do, though, is in maybe 1 minute, kind of introduce, because we have a large diversity in terms of research backgrounds on the panel, kind of introduce your research background and the direction you're coming from to this problem. And then comment a bit or reflect about what does integrative AI mean to you, and where do you think are the things that we should chase are? Like where are the potential big benefits here? So maybe we'll start with Eric.
So I'm Eric Horvath, and I've been long passionate and curious about the foundations of intelligence, computational foundations, which I believe describe both natural intelligence and the machines that we build. Was always deeply interested in how small, simple systems perform well in large-scale, complex, open universes, and machinery that enables these systems to perceive and reflect and make decisions and prosper in potentially competitive environments in the open world, which brings into play uncertainty, notions of utility, actions, and reflection or meta-reasoning. It's been fabulous working in the space of integrative AI. As somebody who has been longing over the years to understand all aspects of machine intelligence and trying to keep track of the best of innovations in each of the fields and subfields, in a world where the CVPR conference has 3,000 people attending and AAAI, the General AI Conference, or IJCAI, maybe has 1,500, you have to sort of really make sure you're dipping into all the areas of expertise and keeping track. But back to this idea of building larger systems that actually have more of the skills that we'd like to see for dreams of building more human-like general intelligences. It's pretty clear that we need to understand how to mesh, weave together multiple competencies and modalities in ways that again, create some sort of a symphony or coordinated intelligence. I've been intrigued in looking at the cognitive psychology literature and looking at models of mind that psychologists have been studying over the years, including the multiple resource theory of mind, which described mind as being not a singular, the singular kind of intelligence we might experience as individuals, but really it's being composed of many experts and ways of coordinating among the expertises. So I tend to look at, on the computational side, at integrative AI as having these three different types of integrations. One I like to think about as fabric level. I often in my mind think about it as representational integration, where there's opportunities to build new kinds of representations and reason over them that bring together modalities that aren't traditionally considered deeply in a unitary, homogeneous framework. And a good example of this is bringing together, whether it be a continuous representation or probabilistic graphical model, fine-grained distinctions about visual and the visual world and language-based semantics in the same representation. I think there's lots of opportunity to do weaves like this that are quite deep in the architecture of our systems, called the fabric level. Then there's popping up a level, this idea of compositional integration, where we actually have components. Some of these are black boxes we heard about in the last meeting. A black box face tracker, spitting out features or confidences, a speech recognition model, an object recognizer, a system that reasons about availability. We have systems that we've composed of these units, and when we do that, we used to end up wrestling with issues of that distributed systems researchers worry about, coordination, timing. But now, subtleties in timing affect deeply user experience. For example, in a dialogue system that Dan and I have worked on, we ended up discovering that we had to introduce a layer of analysis, we'll call it right now, of how long it would take for a pipeline to go from perception to reasoning to reaction, to understand how long it would take from seeing something in a dialogue setting with multi-party to reacting to it and saying something relevant, and running this layer in real, this integrative cross-module analysis in real time, so the system would know to not even attempt to say something. It would take too long and it would just disrupt the conversation. Just hang back now. And understanding that the cost-benefit analysis is a cross component layer that we learn to actually integrate into our systems. Or another example is looking across a pipeline of analysis and looking at all the ways a system could be confused. And we had a project working with an intern last year where an avatar, an embodied agent, would actually share expressions in a natural way, confusion or acknowledgement or relief or surprise, where those kinds of natural status reports about internal state were across modules, across many components, and they all had to share the same language in reporting out confidences, such that the system could have a kind of a natural, unitary, singular sense for reporting on internal state. So I call those kinds of that aspect compositional. And the final area I like to think about is I call reflective. And the prospect of developing new machinery which treats components as object-level reasoners, and the challenge is to reason at the meta level about how, not just to optimize how these components work together, but to even to create new responses by assembling in automated ways through machine learning and through combinatorial search maybe, or simulation, sampling, new approaches by automatically assembling and tuning componentry. And this kind of thing, I think, is getting more and more interesting, because it involves even the idea that someday we might put together a set of components, do a first pass at task-oriented problem solving, and then once we have an up and running system, have it self-optimize with lighting conditions changing, or with dropping a new sensor into the bucket, and having every decision maker, every learner can listen to the reports from that sensor, for example. Components can actually decide what to listen to by doing some value of information analysis in a distributed way. It might be some central ideas as well. But there's a science there of meta-level reflection about componentry, where we don't take it upon ourselves to design these systems really by hand anymore. We take our first pass, and we have this notion of higher level, meta-level processes helping us to integrate and create these integrative models offline or in real time. So I think that those three types of integration are very present, front and central for me when I reflect about the opportunities.
Okay, thank you. So, well, good afternoon. I have laryngitis, but I guess I speak like this. People can hear me through the miracle of microphones. That's great. So I started in AI when what we now call good old-fashioned AI was current AI. And I've been on both the academic side at MIT and WPI, and in the corporate research side at Mitsubishi Electric's Research Lab in Cambridge. I think the reason I was invited to this panel is because for the past number of years, together with my colleague Candy Seidner, who's sitting in the audience, we've been building systems which have dialogue systems, both verbal and nonverbal sides of dialogue, have computer vision, and have manipulation, and have planning, sort of kind of basically the main components. As I was sort of thinking about this panel and listening to the presentations, Eric, you said in your introduction that talk about centripetal forces. I think there's sort of two categories of forces that are driving the field, into separated silos. One is sort of disciplinary, vision people don't talk to language people, don't talk to robotic people, and so on. I think the other one is sort of task-specific focus. So people working on a particular task. Listening to your presentation, Manuela, which I thought was really wonderful, but I did have the feeling that you were really focusing on specific tasks, and you're making progress by being task-specific. So my question for the panel, and the last thing I want to say at this point, is, I was thinking this was a panel on general AI, because there's been this pendulum swing where people sort of regularly bemoan the fact that nobody's working on general AI, right? And now there's this thing, integrative AI, and I'm not entirely clear whether general AI and integrative AI are the same research path, or the same vision, or the same intuition. So I'd like to come back to that.
Yeah, I'd love to hear the comments of the panelists on that topic as well, whether maybe one of them can provide a path to the other, maybe not. I don't know.
Kind of depends what you're interested in. I mean, I think some people may be interested in one and not the other. I don't know.
Yeah.
My name is Li Dongzhou. I want to start with a confession that I'm not one of those cool AI scientists like the rest of the panelists. I'm actually a boring system guy, trying to blend in as into this group of people. And so the only thing that I can remember, doing before I talked to Dan and Eric and the other AI researchers in MSR, is probably that I helped my 10-year-old with his robotics project. That's the only AI exposure that I had. And so, but we do also differently kind of cool projects in systems. So I mentioned two of them as they're sort of related to the discussion in this context. When before Dan and I actually talked about some of the AI problems that they were facing. So I was actually working on, with some of the product teams on large-scale streaming systems where we can process petabytes of data daily and on thousands of machines. And the other project that we did was we can do graph processing of 1 trillion edge kind of graph on only 64 machines within minutes. So we were pretty happy. In systems, that's what we tend to focus on: performance, scalability, reliability, and so on. And then by accident, we were talking about some of the side project that Dan and Eric and others have been working on. Initially, so my first reaction was, great. What about offering you a powerful system or infrastructure that's orders of magnitude than what you have? Would that change your thinking, right? So that's the typical way of system trying to enable disruptions in other fields. And then when we talk deeper about some of the issues, it just strikes me that it's not really about the raw capabilities that system provides. It's really about, first of all, there's a gap between what system provides and in terms of what AI researchers need. And there's also, very importantly, the way of thinking. So in systems, we also reach a point where we're no longer able to define precisely what a system is able to do. I mean, we're dealing with a very large-scale system with a very complicated set of components interacting together. I mean, just like when Yoran was saying, it's very hard to know really what's going on. And in some sense, we're also looking for a different methodology and different way of looking at systems and how they can. We have been dealing with components and abstractions and so on. But the methodology we've been using, try to precisely define what system does, is probably not going to scale very well. So this is why I think putting AI and system together could actually potentially bring disruptions in both fields. This is why I'm very excited to be working with Dan and Eric on some aspects of Psi. Especially introducing capabilities into systems that were never available before. One of the things that we tend to do is essentially the AI researchers should not spend a lot of time dealing with infrastructure problems, right? The infrastructure should provide all the abstractions for them to look at the data, look at how systems behave, and ask all those scientific questions and come up with new theories. And I think this is going to be a very exciting sort of collaboration. I'm actually looking forward to that. And my hope is, in maybe this year, it's kind of strange to have a system person on the panel of AI topic, but a year or maybe a couple of years later, it's natural to have system people and AI people actually working together. So that's why I'm here.
Very
Thanks.
good. Thanks.
All right, I'm Larry Zitnik. I guess even in high school and as an undergrad, I remember just being fascinated by AI and reading like the pop science books on AI and just thinking about how cool it was. And then I got to grad school, and even though Manuela was on my thesis committee, I kind of did what everybody does in grad school and kind of narrowed my focus, and I became a hardcore computer vision researcher working on stereo vision. And I'm going to solve that problem. And I think sometime after my thesis was done, I realized that who cares about stereo? It's going to be solved by lasers anyway. So there's no point. Sorry, I didn't mean to insult anybody. So I stopped working on that problem. But it's still, the desire to do something in AI was still there. But something happened, I'd say 4 or 5 years ago. And it's amazing how these seemingly kind of small things can make a big difference. Mechanical Turk. It's just huge. The fact that people upload their photos, 2 billion or 10 billion of them per day, is huge. The amount of data we have on the web is huge. It's just all these things together. And then deep learning gets into the mix. And we see this transformation just coming. And it's just right now. I don't think there's been a more exciting time to work in AI than right now. I mean, this is like a kid in a candy store all over again. We can start thinking about these higher level problems. So that's why I'm so excited right now. Now, this integrative AI just makes me like bust up laughing. I think it says more about where we've been than where we're going. The fact that we need to put the word integrative in front of AI implies that before we were not doing integrative AI, which seems really ludicrous because intelligence, by essence, should be integrative. It should be general. The fact that we have to put general in front of AI is odd as well. I look at that as more like, yeah, obviously we should be doing it integrative, but maybe we should put more emphasis on it now because now is a time where we have to come out of our silos, going forward.
Cool. Well, thanks everyone for these initial reflections. I don't know if anyone wants to ask a question right now or
A couple comments.
Yeah, there's some comments from the panel.
Yeah, I think that there's something different, Larry, from my point of view, in saying, well, of course, it should have been integrated. Maybe it says something about things being separate. On the other hand, the situation is one where we can reflect pretty deeply about the interfaces and methodologies and the nature of the integration itself as something very explicit. So in some ways, maybe there's a fortunate aspect of the fact that we have modules and components that are sometimes segmented by modality or task or by type of representation with some good competencies and characterizations now in themselves, that there is an opportunity to think clearly with that kind of abstraction layer at what it means to put things together in new kinds of ways. So it's not just the coming back of what it should have been, but also the idea of this notion that there's something about science and the engineering in terms of how do you put things together, where the how itself is part of the science.
I think we originally wanted to. Well, I wasn't around, but I'm assuming that the folks back then, they wanted to go there. And I think right now, the fact that things kind of work-ish, allows us to finally start studying these problems. And the fact that, why do we want things to be integrated? Well, we need to have a deeper understanding of them, right? And we don't have a deep understanding of what these what these semantic concepts mean, like I was talking about in my talk, without having this integrative approach, without going multimodality and that sort of thing. But.
So I think I hear people talking actually in two different things. Part of when you talk, Eric and Manuela, what I hear a lot, it would be like standards. The reason we can't put things together is we don't have standards. I mean, it's not a fancy word, but certainly the system people know all about standards. That's how things get put together. And standards are basically a following activity. Standards are supposed to capture what everybody already agrees on, that then is support for going further. But it's a following, least common denominator kind of thing. That's nice. I'm all for standards.
I don't think I meant that, by the way.
Well, but I think. Well, but I think.
I don't call conceptual interfaces standards.
Well,
understanding how things go together.
That's exactly the thing. But then on the other side of your mouth, or the other side of the panel, when it talks about deeper understanding and conceptualism, and those are leading concepts. We don't even agree, all of us, on how to think more deeply. And so it's sort of premature, for example. So if you want to stick things together that are black boxes or gray boxes or whatever, that's a software engineering, it's a standards issue. And if you want to have languages that support certainty and streams, great idea, terrific idea, because that's sort of saying that it's a least common denominator. Everybody is using uncertainty. Everybody is using time sequences. So for God's sakes, let's not reinvent that. Let's have a standard one. Let's make it available to everybody, and that will help advance the field. No question about that. But it's a following kind of activity.
I'm talking about dropping a new camera into an operating system, a system that's operating, doing stuff in the real world, and having features streamed to the right components and understand what it means to do that.
Yeah, but that's not the same as what Larry's saying. He's asking a very general question about what is understanding. Core AI, general AI kind of question. And so it's good that we have diversity here, but I really think that one's a leading topic and the other's a following topic, I think.
If I may interject in here, I mean, one question is there really like an opposition here, or like
It's all good stuff.
Not in the sense that it's good or bad, but in the sense I'm wondering whether one might provide the path to the other. Yes, we've all been striving for general AI. We have evidence from cognitive science and so on that systems that do these things, existence proof that we have, the brain, are tightly integrated and coupled.
Of course, but it's a different discussion entirely. They put in platforms and fabrics that are going to stop us from wasting our time so we can work more on the hard problems we don't know how to do yet. And not everybody redo the things that pretty much we all know how to do. That's a different discussion than how do we get progress, shared progress, community standards, shared databases, all those kinds of things to get us fundamentally forward. It's not just to me, the problem is not just putting together all the things that people have written papers about. I think we don't begin to know how to do AI. And that's, maybe I'm wrong,
so let me go back to Larry again. What I was saying, fine-grained integrative AI, talking about bringing modalities that have not been brought together clearly in the past in some ways, in new ways, to understand. I was talking about a W3C standard. I meant we're asking a basic question here. We're looking at what's the integrative aspects of this, where I guess you might say we're taking deep understandings about wedges that have been largely modular and separate. We're bringing them together and we're saying we have a real interesting challenge problem of something we'll call understanding right now. Might be describe the intention of the humans in this picture. What's happened, or describe what will happen next. And we find this is a really interesting, hard problem that for which we can leverage existing assets that weren't thought about together before. And it so happens we're in a world where there's some really great work that's been done separately. Now, I haven't mentioned anything about standards or fabrics or sharing. Talking about a hard AI problem, and we're suggesting in this panel, I think in part, and in the last session, that we can make a leap towards more powerful systems along the lines of the basic questions that we've all been asking, through thinking integratively and then even thinking about what that actually means and what the various what's the ontology of integration we can do, and why do we even call it integration? And I actually like Larry's comment when he made the comment, well, boy, it's like we've always been building systems and thinking about systems and interactions of components and modularity and independence, and what that means in these complicated pipelines. So what does it mean to start thinking anew with this new phrase and a track at the Faculty Summit on Integrative AI? Well, I think it means some things, and it does reflect us a little bit about where we're coming from. But it doesn't mean we can't ask basic questions about thinking anew about, for example, what does it mean to take two modules that do visual and the language processing, and without breaking them open completely and rebuilding them, have them talk in a very interesting way where the talking itself is part of the excitement in what might give us more general principles about an AI system.
Well, there's something that's happening, I think, right now, and there's been a philosophical shift, especially in the computer vision community, where thinking about things as separate systems that we need to tie together is very uncool. Especially the image captioning, right? If you have a different module for every single component, people are like, oh, it's a pipeline system. This isn't, that's just a bunch of things taped together. That's not what we want to do. What we want to do is we want to do end-to-end learning, which has only become possible, because of the deep learning kind of revolution, right? And it's amazing that you can actually do this. And I think that's, once you start thinking about, hey, I'm not training these separate modules anymore. I'm not thinking about the problem like that anymore. I'm thinking about the problem holistically. I'm trying to think of a function in which, if I train to try to produce these words, will actually train my visual receptors as well. Right? And the signals are going every which way. Yeah, you could break it up into different things, but the representations become more opaque in a way, which is unfortunate. But it's a different way of thinking about things. And I don't think, it's just, it's beginning to catch on.
Also, this interesting question. Oh,
get the audience.
Yeah. If we have questions, do we have questions right now?
Chris. Hi, Chris.
Chris. Yeah. Can we bring a microphone there?
It's a race.
And Candy was. Yeah.
So I want to kind of reinforce Larry's comment about not so much stitching together the modules and maintaining a pipeline, but maybe better coordinated, because when I went to trying to move from knowledge-based understanding to memory-based, or as tied into a learning system, it was like merging companies. I actually ended up firing a lot of modules that I had because I needed to integrate the operations that were happening into a coordinated single system, an algorithm operating on top of united knowledge structures, rather than these separate silos of knowledge that were then talking in some intelligent way to each other. So I think that I tend to think, when I think integrative AI, I think of, at some point when we understand what goes on, now we realize when we put them together, it's going to be one thing doing it, but capturing a lot of the same operations and functionality that was done in separate ways before.
Very interesting. Can I ask respond and ask a question back to the audience? When is it the case that even in the long term, it will make sense for a system's own reflection about its operation to have separate modules that are relatively well characterized or learnable, and then harnessed in a larger system that learns how to use them, as opposed to big innovations that solve everything in one place. Evolutionarily, you might make the comment that there are mechanisms and machinery in nervous systems that have evolved in a long history of a trail of innovation where there was no way to go back and fix and start over again, but instead layer and do control and optimization. And so there might be something to be said about that kind of thing, even though we would want, of course, to have big grand unifications, unified representations, unified inferential schemes. Just like a high-level comment on your reaction.
Evolved systems are not modular either. I mean, so
they're quite modular.
No, they're quite unmodular. They're layered. You have a reptile. You got the mammal brain on top of the reptile brain, but they all do.
I view layers as modules.
Well, I don't think so at all.
We'll take that. We'll take this to dinner conversation.
I don't think so.
That's a question.
They're composable.
So building on, I think it's a mistake to think about the problem, right? I mean, the whole point about intelligent systems is, organisms have multiple problems. They're constantly doing a mix of things. They're constantly changing. As Dan brought up in the last session, one of the big important problems is longevity and lifelong learning. And so imagine a system now where instead of most of what it knows it started out with or was done through explicit training, but most of what it knows actually has come from its experience with no one looking at its internals. That's something I don't think we know how to build right now. And that's, I think, one of the next really big key things we have to strive for.
One other comment in response to you, Ken, also, and Chris, and back to Tuck, is that an example that Nuria Oliver and I built when she was with us at Microsoft Research, a system called SEER, which was a multi-layered HMM system for recognizing office activities. And once we built this system, we recognized that because of the layering, we could retrain it for different offices very quickly by just retraining the bottom layer, the sensory layer, and with a much smaller parameter space than we would if we had one big network. So back to this idea of flexibility in different environments and lifelongedness through trials and tribulations, there are some architectures that might decompose in a way where the hardness of the problem is simplified in a particular region, and still giving the overall architecture, the sort of a good performance.
So, I want to give Larry a chance to respond briefly to that, and then we have a couple of questions hanging in the audience. So
there's a lot to comment. I'll be really quick, though.
No. Learn from scratch, from the pixel all the way.
One thing I think is important is we say modularity as in the modularity has to occur because that's done by hand. We say we should have a face detector, we should have an orange ball detector, that sort of thing. But a lot of times, even with these neural networks, a lot of times you get modularity by, it just happens. It just learns that this part of the network does this part of the network does that. When they separated the network into two GPUs, they learned separate pathways. One GPU focused on black and white, the other one focused on color. So this can happen just automatically. The other thing is you bring up this point of generalizability. One of the amazing successes, I think, of recent is that our data sets have gotten so complex and so real-world-ish that the features that we're learning are actually, they do generalize. I mean, you look at the number of papers right now that take ImageNet, they train this really super deep neural network on ImageNet, and then they take their own task and they just fine-tune, they just tweak the weights a little bit with a much smaller data set, and wow, beats everything out there. So there is something that is learned. There is something that is general, and we should take advantage of that. And it is amazing what you can learn when you take kind of a relatively weak signal and you backpropagate it through. So,
Let's take a couple of quick questions.
So actually the first part of Larry's comment, sorry, Chris Bishop at the back here. The first part of your comment, Larry, just beautifully anticipated the question that I've been waiting a couple of minutes to ask, which is really to question the whole premise of this panel, that whether you should be talking about integrative AI at all, but rather thinking about things back to front. So we know the brain has these modularity and different kinds of architectures, but they're sort of historical in nature. I mean, the most recent layer is cortex, and cortex seems to be the same throughout, whether it's doing sort of motor or sensory or what particular sensory inputs are. And so really, shouldn't we be thinking about finding out what that sort of general neural goop is? And then the modularity will, the integrative part will happen automatically. The modules, as you say, will arise automatically. I'm not a neuroscientist, but my understanding is that if even as an adult, even if you say lose your eyesight, that cortex that was previously doing visual processing, that some of it can actually be repurposed to process different kinds of signals. So it's somehow not only a single general purpose architecture, but it's adaptive and plastic even during life. So maybe we don't need to worry about integrative AI at all. We need to find the general neural goop, send all the signals in at one end, the outputs the other end, and it will organize itself into the right kinds of modules. Is that completely crazy?
It's great. It's great.
Like
But
No. So
conceptually great.
I think that is one of the big challenges right now, is what is the structure which will allow some of these things to arise. And I think there was a lot of hype for everybody familiar with LSTMs, long short-term memory, that this could do amazing things. It's a recurrent neural network that can learn all these different properties. And I think right now they're kind of overhyped. And I think in the image captioning space, there's a lot of magic attributed to the use of LSTMs. But then when you actually go and see what they're literally doing, it's not that impressive. So I think we still have a long way to go, but I think that is a viable and a good way of thinking about this problem. Not that people shouldn't do it other ways, but there's a lot of potential there.
There's
Pedro.
a question waiting back there.
So, as a starting point, I don't know AI. After yesterday's panel, I want to make sure I'm framing this question as best I can, not really knowing this research space. I am a systems person, and I build custom compute solutions for challenging problems. And AI seems like a very good toolkit to be using for some of these challenges. Is this microphone on?
Mm-hmm.
Yes, okay, good. I wasn't sure. So where my question is going is, I do know something about algorithms, and one of the things we would look at would be looking at distributed learning. So for example, distributed intelligence, bees, ants, things like that, versus, well, go back to the dinosaurs, 2 different brains, one to operate the back end, one to operate the front end, for lack of a better way of putting it. And where I'm going with this is, when I think modular, I tend to think more in that sense. And so I wonder, how can that actually grow into that space, or can your approaches and techniques work within that kind of computing physical framework in a good way and grow to learn more in that sense? And I really hope that I didn't offend anyone in the way I tried to word that question.
What was the question?
It's great. I mean, maybe Li Dong, you can respond, because you've been looking at some of the AI techniques lately, and you're a systems person, so maybe you can.
Right. So I'm trying to understand the question precisely. Basically, I'm a systems person, and we're being actually also looking at distributed algorithms and how we implement those abstractions and so on. So my understanding is you're looking at the problem from like swarm intelligence kind of point of view, where you have a lot of small components that interact with each other, and then there's emergent behavior coming out of it. And I think, so we actually looked at this domain a while back. One thing that always puzzles me is I guess from a system point of view, we want to understand what behavior will come out of those interactions, and it's very hard for us to specify certain behavior and figure out what the algorithm should be in order to achieve that kind of behavior. And I think currently we're actually looking at a very different approach, where we really want to introduce this kind of distributed learning into even an existing system, where the idea of doing introspection in the systems and introducing feedbacks in the system and continuously learning and adjusting and see where this is going. So this approach, because we know what the goals are, and essentially it's we have metrics that can guide the learning process, and that's my understanding of what we have been looking into. So I don't know whether the same approach can be taken in swarm intelligence kind of domain. I don't know enough actually to comment on that.
So it's interesting, this notion of integration, right? Like I think Eric outlined these like 3 different levels of thinking about it. One being some sort of representational, right, where you fuse representations and construct things that maybe get us closer to coming up with things that can support common sense reasoning and aspects like that. The compositional integration and then the reflective, which is what you're talking about, right? Like these systems that reflect upon themselves, upon their own structure. One question that I had is whether there's other kinds of integration or other kinds of achieving these cumulative effects where you might get a benefit, where you get a whole that's larger than the sum of the parts. For instance, someone brought the lifelong learning, like over time, like how do we build systems that do that kind of, and over time and space, like at web scale, right? I was reading recently about robot libraries where they learn tasks from each other. Is there a space where we can think about integration at sort of like at that kind of scale? Like is that I don't know, an interesting direction for AI or?
I have a comment on, it's a little bit off to the nose. Grab
That's
that
okay.
one. No,
Yeah.
grab that one. So first of all, I wanted to say, maybe I sounded perhaps like I was criticizing you, Manuel, which I apologize, I didn't mean to.
Oh, no.
I think that I completely agree with
I'm
you.
used to it.
Part of what integrative AI is about, I think, is as much as possible, no one should go too far without actually putting together a complete system that does something actually in the world, right? I mean, if you do that, it just keeps you honest. And I mean, if anybody disagrees with that, I don't know even what to say to them anymore, because you just got to live in this world and know that how helpful it is to build real systems and have them out. So I don't find that controversial at all. Thinking about integration, I have a little bit of a historical footnote that just came to my mind, which is, remember, I don't know, is it 15 years ago, maybe it's 25 years ago, blackboard systems. Now, I think when people first introduced blackboard systems, you were there, I think they were saying a lot of the same things. That was the way you made integrative AI. Wasn't that the whole idea of blackboard systems?
I think so.
So here we are again, and I don't have an answer. It's a question. If we reflect back on that, did it succeed? What can we learn from that run at this goal?
Let me flip it around. You're
Say it
saying,
better.
why don't we have knowledge in a form that computers can use?
Exactly.
Right? Another way you could
Knowledge,
say that is,
algorithms.
why can't robots use the knowledge that's already in a form that humans can use? Right? And I think the reason why computers have such a hard time understanding this human form of knowledge is that computers don't abstract knowledge in the same way that humans do. They can't deal with abstraction. They can't generalize nearly as well. If you look at, what is the Achilles heel of deep learning? The Achilles heel is that you need huge amounts of data to do learning with it. And that's also what, we were talking about lifelong learning. That's when you're like, yeah, it'd be really great, but it would learn something in about 2 years. And then, it would take so much data for it to redo its processing to actually then change its actions in the real world. It'd be, not a very smart robot. So I think that's like a big challenge, is how do we take these, the computers which are good now at doing these intuitive tasks and making it being able to abstract, being able to reason with the same sort of power that humans have, so that way we can,
So let me mention a question to the audience and to our panel, which is methodological and maybe philosophical. Getting back to what Chris Bishop was saying about cortex and, pursuing as a methodology the singular GOP for multi-layered units that to do everything, where the GOP includes some set of basic procedures for things like back-propagating signal and doing it efficiently, and we're done. Just get there. And so there's 2 comments there. One is that even if that was possible, and that's the feasible philosophic direction where things are heading, and they should head in that way, I'm speculating, let's say that was true, there's the pathway for getting there, the comprehensible pathway for getting there. First of all, neural nets are not, in computation, are not like brain units. And we should start saying that. I mean,
neural out of it.
Oh, Larry likes them.
I mean, there's a lot of mystery about how the brain works that we do not understand. It might turn out that the way to seek understanding is, if that indeed is useful, it could be through things like computational neural nets. That's the methodology we want to play with to understand. There might be some analogous kinds of procedures and processes that are useful to understand for understanding richer, deeper intelligence of the form represented by these naturally evolved nervous systems. But, one of the big challenges with the neural net research as we know it today is inspectability, clarity, comprehensibility, understanding some details, such that when folks like Matt Zeiler and Rob Fergus came up with some basic visualizations, they made some big strides. Along the same lines, it might turn out that the best way for us to gain comprehension and to make leaps to the next step would be through taking modules we understand relatively well, and this includes LSTMs and convolutional neural nets of various kinds, because we understand them at some level, and start pulling them together in ways, for example, to do planning systems. Can you imagine trying to solve poker with a deep neural net the way that Mike Bowling and others did at Alberta? There's more going on with thinking, reasoning, reflection that we have no idea how to do with this GOP. So I want to raise the question to the academic community and to our partners on methodology with, is the short path to deep intelligences of the form that the founding fathers and mothers of AI reflected about solely through really pushing hard on where we've seen some recent gains in classification technologies, or not? And if not, well, hang on. If not, why not? And what role does this approach to taking various kinds of modules, including strip-style logic that we understand, and thinking through building larger systems that can do more kinds of tasks and generalize and abstract? So just a question I want to ask everybody on it, given the fact that we're kind of getting to a GOP-like, let's stop now, state in this room.
Pedro had a question.
Sorry.
Yeah. So this question actually goes back to something that Manuela said at the very beginning. Building complete agents has been a theme in AI from the early days, continuously. People have never stopped trying to do that. And I think we need to ask ourselves why there has been a lot more progress in developing individual, solving individual problems like classification or stereo or whatever, than in putting the elements together. And I think the number one reason is what Henry Kautz calls the complexity monster, right? You have a lot of things that work well individually, and then when you put them together, they don't. This is what kills us. And we can make all the progress that we want on these individual things. If we don't solve that problem, we will never have intelligent agents. And I think Manuela, to my mind at least, gave a hint of an answer to this when she talked about we need to make sure, this is sort of like, we need to make sure that each module or whatever, or each capability can do its thing with input from the others while knowing as little as possible about them.
Right.
But the problem is that this can't be the whole answer, because in a way that's what every well-designed system does. It's called divide and conquer. My procedure has its internal state, and in some sense it seems that the real difficulty in AI that has stumped us for 50 years is that divide and conquer doesn't work for AI, because the interactions between the modules are too broad and too deep. So in some sense, maybe we need a new kind of design paradigm that is different from how we build our systems today. And I wonder what that would be, and what the panelists think about this.
I'd like to speak for a minority that isn't present, except maybe for Ken Forbes, which is a small group of people in AI who work on what are called cognitive architectures. It's not very fashionable, but in some sense, they're trying to integrate, and maybe we just think that they're just never going to get anywhere. And they do sometimes build complete end-to-end systems, but at least they're thinking about the issue of what are the architectural principles and variants. But they don't talk like software engineers. I'm a software engineer actually originally, and they don't talk about modules and APIs and data pipelines and so on. They're mostly talking about shared representations. They're mostly talking about sort of the the real-time loops and how many there are, and so they're talking about architecture, something that any systems person would recognize as architecture, but they're influenced by human architecture. I mean, they take their inspiration. Some literally do fMRI studies, but all of them take their inspiration from what's known about human cognitive architecture, and that's a part of AI which is not represented on this panel, and I think very little represented in this room, that I think are trying to work on integrative AI at the architecture level,
Well,
and they talk about it very
Is
differently.
that number for Ken over there?
Yeah.
No, but
So I just want to speak for that.
Waving over
I want
there.
to speak for that contingent because I think it's important.
but
Yes, so that's actually one of the things that I've learned, interacting with the AI researchers. In systems, we tend to have, deterministic, modular kind of design. So everything is sort of designed, right? You have interface that, you expect the other component to do in a certain way. And in the AI domain, this is completely not true anymore. So this is why, you really need to design the system as you said, in a completely different way. And this is, what I think is very exciting also, from system point of view. The other thing that I want to point out is, I think the capability of what systems can do nowadays is also a major factor. Now there's this potential for disruption. Previously, if we only have the capability to do one component at a time, and all the interactions requires a lot of additional computational resources to handle, and it's just not possible to think about integrative AI and those kind of things. So I think there's a timing issue as well, where we now have maybe hopefully deeper understanding of how those components work, or how the existing robotics work, and coupled with much more powerful hardware and more data and so on. So this is where I think why we have general AI coming back again. It might be different. I don't know what the breadboard system did, but timing has to be right for those things to have the right solution.
Question there. There's a question that's been hanging for a while. Yeah.
It's not a question, really.
Comment.
So this might sound boring. I'm not really that interested in the architecture or the representation, but what I love about the work that the folks on stage do is that you build systems that do a task that I can kind of understand or wrap my hands around. It's a task that seems like a sensible task. It might be an artificial task, but it's still a task that has some of the right properties that we want an intelligent thing to be able to do. And I think that, I think when I look at Manuela's, the whole discussion you had about finding flat surfaces, and the vision system is tuned to find flat surfaces because you're navigating an environment, a built environment that has a lot of flat surfaces, and that's kind of an input constraint that you're aware of, and the output constraint is you don't want it to bump into the wall. So you have a pretty clear set of constraints there, but what I like about what you're doing is you're aware of those constraints. They come from, you have a pretty clear understanding of the environment and what it's bringing and the task and what it's bringing. And, I think the question, Eric, you said something like, when will categorization, what if it's all just categorization? And I guess I would say categorization of what for what? And I think that was really the thing about all the work on image captioning. And Larry, I think you're a sweet guy, but I found your work very compelling, partly because to me it was just very clear that in that work there was very little understanding of the social constraints on the input pictures that have been garnered from the world and how regularized they are and how non-generative that input is, and actually how non-generative the output is as well. That the captions are just so, darn simplified in some sense. And I mean, it raises the question of what do people, when they apply a caption to a picture, think they're doing? But most of the people doing that work, I don't think really worry about that very much, and that's actually what makes it a bad task for AI from my perspective. I'm not saying it's a bad task for computer science, or even really from AI from an applied perspective, or even from pushing those particular technologies forward, but it's hard for me to see how to generalize the results of that into something that I can use in a more profound way.
What's your favorite task?
Telling stories, of course.
Actually, baseball games, Little League baseball games.
I will say, no, actually, I have a quick thing. I was talking to somebody who does this kind of, who does a lot of work on optimization for image things. And I said, what I'm really excited about is the idea of eventually looking at a picture and telling a story. And this guy said, yeah, we're doing that. I said, really? It's not just, you mean like labels? And he said, no, we can look at a picture and say it's people sitting around a table eating dinner. And I said, that's not a story. And then we had a whole, and I actually ended up having to say to him, do you think it would be strange if you're trying to design a computer program to have some kind of characterization of what the output of the program actually is supposed to be? And I found it strange to have to be able to say something like that to a computer scientist, I'll be honest with you.
A couple points I want to make. One is, I think the story generation, once people actually started hitting on it, might not be as AI complete as we hope. And I think it is a huge, if people care about integrative AI and they want the field to go in that direction, one of the biggest challenges is coming up with challenges that people want to solve. And it's not just coming up with a challenge, it's coming up with the data that goes with that challenge and making sure the data isn't built in such a way that it biases it towards like deep learning and that sort of thing. So there's so much thought that needs to go into developing challenge, the right data. With Coco, should we get a more diverse set of images so that way we see things generalize? All these things are incredibly important. One comment I want to make, it touches on a couple things you guys said, but I think having something be interpretable is it's completely oversold, right? I think Dan and I argue about this all the time. He has these systems, he has each box, and it's exactly what each box does. I don't think that is necessary, and I think it's actually misguided. And I think in computer vision, you can look at you can look at an example of this. We, for decades, tried to make our features interpretable because we designed them by hand, right? And we said, we need edge filters, and we got to a certain point because we could do introspection, we could kind of think what would be good. Then we got to a certain point, and we're like, I have no idea what to do from here. Well, I could look at parallel lines maybe, or T-junctions, or, and you add these things in, and each one gave you just like such a small little minor delta that you could never publish a paper on it, right? And you're just stuck. You're stuck at this one level. And then we said, I don't care anymore. And, basically, let the algorithm learn. You can't really, we can kind of interpret what it's doing, but what it did is it just freed us from having to interpret what it's doing, and it did something that's more intelligent than what we were doing by hand. And I don't think this is just limited to, the V4 and V3 levels of the visual cortex. I think it's true for all the different levels and how they interact with each other. We need to let go of this interpretability. We don't understand how humans work.
But Larry, let me say something about this. Without interpretability of your software, of your algorithms, of what backpropagation does, what it means, you're stuck. You're stuck with where you are and what you know, and that's solving a problem down here, which finding features for you. That was a great problem to solve. How about going beyond that now? You need to know what your algorithms are doing.
It's not a science. It's an engineering.
But you need to have some handles to go forward and make progress. You need to continue to be aware and be able to reflect about the actual problem.
No, I actually completely agree. I'm just, what I meant there is interpretability is actually great for the science, to really understand what's going on. Scientists. Well, yeah. To get a deeper understanding. And I think that's important. We should be doing that. But I think in this field, we'll actually find that the understanding will come after the engineering part of it, where we actually design it and it works.
If you have a direction that you know where you're going in engineering, though. You have to, how are you going to engineer knowing where you're going?
When you do graduate student gradient descent, right, then they're just trying these like random algorithms.
Big search space.
Yeah, it's a big search space.
I know they are, but I think I'm afraid this has been a fascinating discussion. Maybe we'll take one more quick question, and then I want to give everyone a chance, because we're getting close to the end, to reflect in the last 2 minutes some final thoughts. But let's take one question. Candy.
I would like the rich panel to react to one concept or term which probably I find is missing. We discussed from deep learning to vision to knowledge, representation, common sense, everything. I want the panel to react to one simple term called memory. Now, from architecture and system guys, it's just a lookup table, because you just give an address and the contents come out. That's what memory is taught in basic computer science. But I'm sorry, cognitive psychologists say learning and memory goes together, and there are concepts of short-term memory, long-term memory, which I am not sure whether models have been tried out to make intelligent systems, and maybe that's missing somewhere. Could you kindly react to that?
Not in vogue.
It's a very good question.
Are you a cognitive scientist?
It doesn't matter what he is.
You just, right. Well, so that's just not in vogue at the moment. So I was trying to speak for that thing. Yes, people certainly are trying to be inspired by cognitive psychology and build computational models that are inspired by that. And they're not coming up with the best results to get onto the news at the moment.
Thanks, Manuel. So I want to invite the other members of the panel to kind of close off with some parting thoughts, and maybe, what do you, one direction might be to talk about what do you think we should do more of maybe next if we're pursuing this big dream?
So I can just follow up to Manel's point. From a system point of view, I've seen that we have been living in a digital world where everything is sort of precise and we have complete knowledge and everything is sort of deterministic and predictable. We're certainly going out of that world now, and we're seeing more uncertainty, even in the digital world, and of course, when we interact with the real world. This is going to significantly change how we build systems and how we, what kind of capabilities we need to have. It's not just about performance, not about correctness, and not about being predictable and so on. And I think that is, to me, a fundamental change in how we approach systems. And this is why I see a lot of opportunities in combining systems and AI together. And what are the core principles in systems that will still be useful and applicable, and what are the concepts of AI that actually can be integrated in all the systems that we build. And I think that it really excites me.
I just want to comment really quick on the long short-term memory thing. I think the short-term memory is one of the most exciting areas right now, and being able to take short-term memory and reason on that, and then how do you bring this long-term memory concept and put it in the short-term memory? How do you remember what you've said previously? All of that is just amazingly fascinating right now. And if you look at, I know I've been harping on neural networks too much, but a lot of people have been thinking about those sort of things in that context. And I think, to me, it's incredibly exciting. Now, going forward, if we really want to, push integrative AI and where can it go? I mean, the data sets we talked about before, I think are incredibly critical. Designing data sets, designing problems, which are really difficult to solve it's really hard to cheat, right? The captioning task, you can cheat. The image classification task, it's not integrative, right? So that's one thing we like about the visual QA. It'll be interesting. If people can cheat and there's a way around it without solving the general AI problem, people will do it. And no matter what you do, even storytelling, people will figure out a way to do it which cheats, right? But we can do our best. Yeah. And I think in designing data sets and designing problems, we can do our best. And then finally, I think for a lot of this, it's really interesting to think about how do we scale, right? How can we take our ideas with these robots and make them, and I think they're doing this with the grasping, where they're having, not just one robot in one lab learning how to grasp, but they're doing it across robots all over, the U.S. learning how to grasp. How can we get more data? Yes. And maybe we can't do it with real robots. Maybe we do need to do it with some, artificial, something or other. But I think once we start thinking about scaling and once we start thinking about how to, do it big, then I think the field will really see a lot of progress.
I'll leave Eric the last word, so I'll speak now if that's all right. So actually, I want to just put another chip on your point, Larry. As I think about what useful we could say as opposed to all this sort of philosophical BS we've been doing, I've been continually impressed, more and more so, your work among others, with the leverage that well-chosen challenge problems, shared problems that the community buys into. And what I really like is that you then modified it. You discovered that there was a cheat, there was a exploit in the thing, and then you keep changing it. And so I think that if we really want to advance integrative AI, other than building lots of systems, continue to build them, of course, absolutely. But I don't think that just choosing good applications and then making them bigger and talk to each other and so on, I don't think that by itself is going to get us there. I think that if you want to really pull the field, I put my vote on thinking about good challenge problems and problem sets. I just think that's the most useful thing that could possibly come out of this discussion.
Yeah. Challenge problems, yeah.
So my one reflection I'll share is that it's an interesting time where we're seeing some very exciting specific capabilities and jumps in abilities with lots of economic value to companies coming from a particular methodology. In particular, the convolutional neural net has its re-rised a renaissance of these methodologies with more data and some refinement on, for example, the way we do optimization with them. And I do agree that it would be wonderful, and one potential goal of our mission is to come up with a parsimonious set of principles that explain everything. in a set of n layers and some procedure for walking over and modifying the parameters in those models. I think we should continue along those lines and look very carefully at those successes, but we're not ready to collapse our research yet into one vein or one line of reasoning. And it's important for people in this field to really understand the diversity of methods that have been tried, even in earlier forms, just like neural nets were retried again in the current era, to think deeply about sampling, simulation, planning, some of these core search, some of these core methodologies we know will be important whether or not they're solved magically in a surprising way by a simple representation in the future. So I think it's nice to see this healthy discussion we had just now with them waving our hands. I wouldn't call it BS. It was very interesting and valuable, I think, for sharing intuitions and then thinking about and interpreting what people were saying and reacting. But it's wide open right now as to how it's going to go. And I have lots of questions and curiosities, and certainly those include curiosities about what we're seeing with neural nets and how to visualize better and understand them better and to innovate with them. There are links to rich probabilistic graphical model representations we've had in the past, notions of how we do causal inference. Lots of questions out there and lots of directions to go in. And also the links in what we're doing to cognition, to human cognition, and to what we know about minds, whether abstractly so, oh yeah, they're all neural nets, I think, or in more detail, here's what we found in hippocampus. And so I'll stop there.
Thank you.
Let's thank the panel.